Okay, in this presentation we are going to look at the beta type 2 distribution, which is also known as the beta prime distribution. Now, it's very similar to the beta type 1 distribution, but there are some important differences, and we'll sort of touch on them here. A continuous random variable x is said to have a beta type 2 distribution with parameters alpha and lambda if its PDF is given as follows. Just a sort of quick remark, I'm having sort of typesetting difficulties, so usually I would write them as the parameters as alpha and beta, but just for the sake of clarity and simplicity, I'm just going with lambda here instead. It's a good idea not to be too complacent with regard to notation anyway. So f of x, the PDF, is 1 over the beta function of alpha and lambda times alpha minus 1, x to the power of alpha minus 1 divided by x plus 1 to the power of alpha plus lambda. Now you notice here we have the support, the range of values which this PDF applies to. The range of values is 0 to infinity. The beta type 1 distribution is 0 to 1. So that's the key difference between the beta 1 and the beta type 1 and the beta type 2 distribution. Okay? 0 otherwise. Okay, so yeah, just make a note of that as well. So in notation it can be written as x is distributed as beta 2, variable beta 2, alpha and lambda here. Again, sometimes usually I would write it as beta. Now, the beta function is a key thing here, and that is, first off, in the first instance, that is a multiple of component gamma functions, the gamma function of alpha times the gamma function of lambda divided by the gamma function of alpha plus lambda, and that itself is an integral from 0 to 1 of x to the power of alpha minus 1 times 1 minus x to the power of lambda minus 1. Okay, that is the beta function. Now, we require an alternative formulation. So I'm going to use this one here. Okay, now this is the key thing here really, because this is the formulation of the beta function suits the beta type 2 distribution when you're working with it. The limits of this beta function here are 0 to infinity. We still have x to the power of alpha minus 1, but now we have 1 plus x, okay? Previously we had 1 minus x, to the power of minus alpha plus lambda, okay? So you can also express this as x to the power of alpha minus 1 over 1 plus x to the power, 1 plus x to the power of alpha plus lambda, okay? Now, just a sort of quick remark that we're going to be using the gamma functions here. Gamma functions are straightforward enough. They're essentially using factorials. Just a sort of quick remark, my exclamation marks went wild there, so just ignore those little mistakes. The gamma function of n is n minus 1 factorial. Okay, and they are some sort of little extra results that follow on from that. So the gamma function of 5 is essentially 4 factorial. We are mostly going to deal with it in the context of positive integers. Now, the mean of the beta type 2 distribution, what we have to show is that is the expected value of x equals alpha divided by lambda minus 1. Okay, and you can assume that lambda is not equal to 1. Okay, and in fact you can assume it's greater than 1 actually. But anyway, we'll just keep to the key remark here that we want to demonstrate this. So the expected value of the beta type 2 distribution is given as follows. Essentially what we want to do is calculate the expected value of x, and that is the integral of x times the PDF dx. Okay, so there we have x. We have this beta function here, or this inverse of a beta function, which we're going to take outside the integral. And what we're going to do there is multiply x, this x here, and x to the power of alpha minus 1. Okay, and we're going to re-express that as x to the power of alpha plus 1 minus 1. Okay, why am I doing that? Very particular reason why I'm doing that. Down below, I have x plus 1 to the power of alpha plus lambda. Now what I'm going to do here is express alpha plus lambda as alpha plus 1 and lambda minus 1. Okay, so essentially what we have here is set the integral set up in the context of the alternative beta function, okay, but just the parameters are alpha plus 1, okay, and lambda minus 1, okay. So the two parameters, they essentially form this addition here, okay, the power of the in the denominator. But we also have x to the power of alpha plus 1 minus 1, so the one of the parameters minus 1 in the numerator. So essentially just a sort of manipulation of the structure to suit the expression of it as a beta function. So essentially this entire integral there can be expressed as a beta function of alpha plus 1 and lambda minus 1. So what we're going to do is essentially and that just reverts to a fraction of two beta functions. The beta function of alpha plus 1, lambda minus 1, divided by the beta function of alpha and lambda. Okay, so I'm going to express the numerator here, and I'm going to express it in terms of gamma functions, and I'm going to express the denominator here. I'm just going to invert it. Okay, this is the inversion of the beta function of alpha and lambda. So that's the key part of it there. Alpha and lambda, the gamma function of alpha plus lambda, they cancel out straight away. Okay. The gamma function of alpha plus 1 can be expressed as alpha times gamma function of alpha, okay, and that divides out with that, okay, and the gamma function of, looking over here, the gamma function of lambda can be expressed as lambda minus 1 times the gamma function of lambda minus 1, okay, so that cancels out with that, okay, so we got loads of cancellations, and what we end up with is alpha divided by lambda minus 1. Now we're going to do the variance as well. Same sort of approach here. I'm going to go through this fairly quickly because it's using the exact same sort of concepts really. It's just a little bit longer. The variance of the beta type 2 distribution is the variance of x equals alpha times alpha plus lambda minus 1 divided by lambda minus 1 squared times alpha minus 2. So essentially what we're going to do is use this identity here. Now this is a commonly used identity in probability, so you should really know it at this stage. What we're going to need here is the expected value of x squared. Okay, that's the key part. We already have the expected value of x, we just square that later on. Okay, so the expected value of x, this is the expected value of, is the integral of x squared f of x dx. Okay, and what we're going to do here is I should have this as x squared, little typo there. Okay, and I'm going to multiply this x squared by x to the power of lambda, x to the power of alpha minus 1. But what I'm going to do there is just re-express it as x to the power of alpha plus 2 minus 1. Again, I'm doing the same sort of trick. I'm setting up a new beta function where one of the inputs is alpha plus 2. Down below here, we're just going to express the power there of alpha plus lambda as alpha plus 2 plus lambda minus 2. Okay, so that's just plus 1, plus 2 for the other, plus 2 for one, minus 2 for the other. It's still mathematically the same, but now we have it as alpha plus 2 and lambda minus 2. So that's the beta function there. Beta function of alpha plus 2 and lambda minus 2. And again, we're going to divide that by beta of alpha and lambda. Okay, so same thing as before. Those are just the tricks that we're going to use. The beta function of alpha plus 2 and lambda minus 2 can be written as the gamma function of alpha plus 2 times the gamma function of lambda minus 2 divided by the gamma function of alpha plus lambda. Remember, when you add alpha plus 2 to lambda minus 2, you still get alpha plus lambda. So just in case, this is alpha plus 2 plus lambda minus 2. So it just reverts to alpha plus lambda. That cancels out with that, essentially. So we could just disregard those. Essentially, what we could do here is using the same sort of approach as we did before, re-expressing those gamma functions or factoring them up so that we get cancellations. We should get alpha times alpha plus 1 divided by lambda minus 1 times lambda minus 2. Okay? The alpha minus 1 times alpha minus 2, lambda minus 1 times lambda minus 2 is essentially just re-expressing gamma function of lambda. Okay? Anyway, because that will cancel out with that. So just loads of cancellations, essentially. Okay? Now, the variance is the expected value of x squared minus the expected value of x to be squared. We already seen that that is alpha divided by lambda minus 1. Okay, so square that. What I'm going to do is actually factorize up the first expression, the expected value of x squared. So I'm going to sort of take out a here and lambda minus 1. So I'm going to sort of factorize this essentially. Okay, just to make it a little bit easier. So such that we have alpha divided by lambda minus 1 and this expression here, which is going to be easier to simplify. Okay, we can multiply out the alpha minus divided by lambda minus 1 later on. But essentially what we have here is two fractions that we simply can cross multiply here. Now it's tricky looking, but usually what happens is loads of stuff cancels out. So we have alpha lambda that cancels out with this minus alpha lambda. Minus alpha, that probably stays where it is, plus lambda, minus 1, plus 2. So that plus 2 lambda and that minus lambda just end up as a lambda. Or sorry, minus alpha and plus 2 alpha, that just ends up as an alpha. So that's how it proceeds. It's a little bit tricky, just all these small moving parts, but otherwise the idea is pretty simple, really. So that's it. We'll leave it there.